not the caption contest, the fractal contest. And for that reason, I asked Vanessa, who won, to send me a picture of herself in her new t-shirt. And she agreed I could show this briefly to you all. And so let's take a quick look at the nice picture that she sent. Okay, now, here's Vanessa in her structural induction t-shirt.
Wow.
In California. Pretty nice, huh? You can order these on Cafe Press. Maybe we'll have another contest. So congratulations to Vanessa. Thank you for participating and being a good sport. Pretty nice. I heard someone say, wow, which is exactly how I feel about this. Great, 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 great look. And everyone will ask you what it is. Congratulations, Vanessa. Okay. All right. So where are we in our investigation? So as you know, the midterm was due today. We're going to grade that starting tonight. We're usually pretty quick about that. We might run into issues. If we do, we will let you know. But usually we can grade that pretty quickly. I just wanted to mention, can you all see that this is recording? I don't see that on my screen.
It's recording.
It's recording?
Yeah, I see it on my screen as well.
You're recording? Okay, good. Thank you. Appreciate it. Not sure what's not doing anything than different Zoom interface here. Okay, so that's the update on that. Of course, PS3 is out, and PS4 will have a lot of streams on it, but it's not going out until October 2nd. So today I want to talk about, continue our discussion of streams, and I want to talk in particular about infinite streams, which are pretty cool. So this comes from really the mathematical question, which is, how can we construct and reason about and compute with infinite sets? So we're interested in all sorts of interesting things, like we might be interested in the natural numbers. We might be interested in all of the integers. We might be integers in the rational numbers. All these are infinite sets. They're really quite huge. And conceptually, we might, you can make all sorts of interesting first-class objects in good languages like Scheme. So we'd like to do something like, say, define nat to be the natural numbers. And then we want to do things like pass it to a function. We don't want to say filter, and then some appropriate function, and nat, and have that give us some possibly infinite subset of the natural numbers. And of course, we need the stream version of filter, which I'll denote as filter stream here. So what we need to do, of course, is understand these higher order procedures that work not only on lists, but on streams, like filter stream or stream filter in here. And I need to tell you something about what actually goes in this magic box. Like here I've said nat, a variable is bound to this infinite object, which is the mathematical symbol for natural numbers. That's not actually how we do it. We do it with streams. But the point is that once you have these, you can use them everywhere. You can pass them into functions. You can return them from functions. You can put them in data structures. You can name variables after them. You can combine them. You can operate on them. And even though these objects are infinite, they have all the rights and privileges of almost all other data structures. And so while some of you might actually be pretty good at data structures already, or be coming out in this class, or maybe you took 201, I doubt anyone showed you how to make infinite data structures before, which is really cool. And they directly model the mathematical objects that are infinite. So that's pretty neat. That's what we're going to start talking about today. And of course, in mathematics, there are many infinite objects, not only these, but there are infinite series, for example, and all sorts of interesting first-class objects that can be infinite. So we'll start an investigation of that today. Okay. So I'm also going to talk about some interesting, almost philosophical questions that come up with delayed evaluations, and questions that you really only can get at when you start thinking about functional versus imperative programming in this context. We'll see if we can get to that. We'll leave some of the more complex things to section and sort of set this up. So let's review where we are here. So we introduced a new programming paradigm, although like most things in this class, it's basically mathematics, but we write programs based on that. And streams have the same basic contract as a list. So stream first of stream cons X onto stream returns X, stream rest of stream cons of X onto stream returns stream, but the order of evaluation is different. Stream cons evaluates X immediately and the stream only when it needs it, it's delayed. Whereas stream rest always forces evaluation of the tail of the stream. Now, how do we do delayed evaluation? Well, essentially, like many things in computer science, lambda is the ultimate constructor. Lambda is your friend. So with delayed evaluation, we only compute values in the tail when they're needed. So if you have any expression, which I'll call foo, delay foo returns a promise to compute foo when it's forced to. So it makes something you might call an IOU. For those of you, this is a strange term if English isn't your first language. IOU is supposed to stand for IOU. The usage is actually from about 1850. So you make a promise. So force IOU collects on that promise. And we talked about how to implement that last time in lecture 10 using lambda. And these streams gave us a view of programming that's really quite a bit like signal processing. Now it's discrete, but actually a lot of signal processing is discrete as well once you quantize things. So we have data going through this chain of boxes. So we can ask questions like, hey, what is the second prime between 10,000 and a gazillion? And so we imagine to have a stream on the left going in, the stream of natural numbers between 1,000 and a gazillion, goes into a filter for prime, and then you pick the second one and you give your answer. And the key difference between streams and lists is that with streams, the flow of data is kind of like pulling on a string. You only get as much computation as you need it, as many forces as you do to provide the next output. The computation in a previous box doesn't have to complete before you can start working on the head of the snake that's coming through. But here's the question. If this amazing stream we made basically doesn't do any computation, why do we need that gazillion in there at all? Well, if we were implementing this with lists like we did last time, it would basically just be there to stop the recursion. It keeps the lists finite. It's a very happy place to be. But with stream, the delay has already stopped the recursion. Can't go any further. You're not going to get anything more than the number of forces you do, i.e. the number of stream tails. That's pretty cool. So in this philosophy, we never make more stream until we actually need it. So we don't need another device or trick like having a zillion in there. We don't need that to stop the computation. Delay has already done it. That's pretty neat, actually. So instead, we just make the stream infinitely long, which is pretty cool. Now, what does infinitely long really mean here? What it really means is that whenever you take the tail of it and you ask for the next value, there always will be a next value. And that's really what infinity really means in this context, at least affinity of countable sets. So now we can build on that. Here I can define the integers. So notice, you know, one of the, I think, kind of cool things about this class as opposed to some other math classes, by the way, when I took them, I adored them, was that we get immediate gratification very frequently in this class. So I promised you here that I would do something like define the natural numbers to be something, and what is that something? And you might have thought, oh, I'll have to wait 10 lectures. He's going to make me do all this math. But in fact, we're going to do it immediately here. I'll define the natural numbers using streams. In fact, I'll do it two ways in this lecture. So look what I've done here. I've written a little function here called integers from, and this produces a stream starting at n that enumerates the natural numbers from n just going on up forever. Pretty cool thing. And then I define the integers to be integers from 1. Integers in that sense. So now we have this infinite stream of integers. Now check this out. This is the comparison that is really crucial here. Integers is an infinite stream in the sense that there's always another integer to pull off it. And if you think about it, if you were ever, say, 9 and you had a little brother who wanted to know what infinity was and you had some idea, you might say, well, count as high as you can. Maybe he counts to 3 to 23. And you could say, well, you could always count one higher, right? Any number. That's the basic idea of infinite in this case. There's always one more. But this here is not an infinite loop. You know, there's no call actually executed to integers from 2 because stream cons delays it. So compare this with cons, right? If you were to implement this with cons instead of stream cons, you would absolutely get an infinite loop as soon as you called it. It would just loop forever. But with delay, which is within stream cons, the tail is always delayed. And so you're not going to be able to undo the delay until you call stream rest. which then calls force, which forces the tail. So for every delay, it has to be undone with a force. Okay. Now, what does this object actually look like, right? So now, we've actually done this here. We've defined some code that implements our marvelous thing here, the natural numbers. But we might like to look at a concrete representation of this. Let me do that for you. So I'll draw it. I've also written it out here in case you want to look at it later. So after this, after I've said this, integers is bound to something that looks like this. It's bound to a pair like this, where the head is 1, and the tail is a promise to call ints from on plus 1, 1. And let's put a box around that to make sure we know this is evaluated. And of course, if you wanted to be really careful, you mentioned the 1 is evaluated too. All right, so integers is actually bound to this. Is bound to this cons box here. So this whole business returns a pair basically, and the tail is delayed. So let's print out some of the stream. So essentially what I want to really do here is something like this. I want to do something like map stream, the function print over S, right? But I'm going to actually write it out here. So here's print stream, a little function on stream. What does it do? It prints the head of the stream, and then it calls itself recursively on the tail of the stream, the rest. And this is going to print out the integers. And I've written out what it does here, but I think it's instructive to actually draw it. I mean, it's the same thing, but let's actually do that. So initially, ints is this thing, but int stays bound to this thing here. Ints is this beast I've drawn on the left like this. But what happens in print stream? So the main action in terms of streams and print streams is that we print out the head and we call ourselves recursively on the tail. So we can kind of animate this by writing down here, what am I going to print? And what happens with the data structures. So what happens when we call print stream on integers, I'm going to trace this, is that we're going to print out 1. Why? Well, we're going to get stream first to the stream, that's 1, and we're going to print it. That's pretty straightforward. But now we're going to take stream rest and call ourselves recursively. So what do we do with stream rest? Well, that's the tail of this beast up here, right? And then we're going to force it. So we're going to take the tail and we're going to force this guy. So what is the tail? It's a promise to call ints from on plus 1, 1, right? So let's look back at integers from, which fits nicely on the stream like that. So what happens the next round, this basically the result of the stream rest is going to be something like this. We're going to get a 2 here, and we're going to get a promise to, I'll abbreviate, I'll see ints from, this is not if, but ints from plus 1, 2. And just to keep in mind, promises are evaluated, things like that. So that's the result of the stream rest. Now that's what stream rest returns here in this call here. Now we call print stream again. Print stream then finds the head, which is 2, it prints out 2, and then it takes stream rest of this beast next to the 1 here. How do we take stream rest? Well, we take the tail and we force it. So the tail is the promise, forcing it actually evaluates this, and the next stream rest looks like this. The key thing here is that we're going to evaluate plus 1, 2, and we're going to get 3. And here we're going to have a promise to call ints from on plus 1, 3. And the pattern repeats. So that's an example of an infinite stream being printed out and iterating through a little bit about what happens when we actually call it.
What are we using to force the stream? Which line of code forces?
Sorry, say again?
Which line of code are we using to force the stream?
Forces in stream rest. Look at lecture 10. Stream rest forces the tail. I can write it out for you. Make sense? Hello?
Yes, thank you.
Sure, absolutely. Yeah, I just wanted to, make sure it hadn't dropped. Great question. So yeah, definitely need to understand lecture 10 before understanding lecture 11, but we'll do our best. I'm happy to answer any questions, but that's where we did that. So we defined stream con, stream first, stream rest, all the stream functions that were, used, that I'm not defining, were defined there, and that's where the delays are all hidden. So there'll be no new delays this time, except in examples. I don't need to write new code for this. Okay. All right. So stream functions pretty much make sense on inference streams, methods for streams. So suppose we want to do something like this. We wanted to say something like, hey, let's get all the integers that are divisible by n. So we have a little predicate here, just like you might have had in problem set 2. It checks whether or not x is divisible by n. That's what the predicate divisible does here. And then suppose we wanted a stream of all of the numbers that are divisible by 3. Well, we take the integers down here and we filter it by this predicate here that just checks whether or not a number x is divisible by 3. And after doing this, 3's is a stream with 3 elements, 3, 6, 9, 12, 15, 18. So very convenient to make new streams out of old ones using these higher order functions. So at this point, it's a little bit mind-bending. Print stream is an infinite loop. Thanks to Nicole for the question. And it never stops. But for an illustration, that's fine with us. We gave you, or will give you, in problem set 4, a function you could write yourself called list, stream to list, that takes a stream and an n and gives you the first n elements of the stream in case you ever just want to print a few of them. So one thing that comes up with this is, it's pretty neat. It's infinite in the sense that no matter how much you get out of the stream, there's always going to be more because there are always more numbers that are divisible by 3. But you might ask some questions about this. Are the numbers really there? Well, what does really there mean? It's kind of a mathematical, philosophical question. If you look for those numbers, you will find them. But if you don't look at them, they're not explicitly represented in the computer, not at any rate as numbers. So there's an analogy there. If you've taken some physics, you might know about Heisenberg, right? Heisenberg and the observer problem in quantum mechanics is that you could have a particle, and if you measure, if I'm driving to Charlotte, you can be wondering where I am and how fast I'm going. According to quantum mechanics, if I'm a small particle, you can measure my position, but then you can't know my velocity. If you measure my velocity, you can't know my position. So in some sense, the act of observing certain things in physics actually changes the underlying representation. Similarly, with streams, especially of memoization, the act of actually asking if certain numbers or elements of the stream are there could actually change the representation. So again, you always get more. In that sense, the streams are infinite. Are they really there? Yes, if you look, you'll find them. But if you specifically look under the hood at the underlying representation, they're not explicitly represented as numbers. They're represented in another way, basically as recursive functions. Okay, so we can come back to more of it later when you have a little more experience, but I wanted to sort of talk about this. And I'm happy to engage these questions. They're super interesting, and some people, based on these questions, decide to go on in mathematical computer science and pursue them. So I want to do something a little more cool, interesting. It's pretty easy to count by 3's. You might not even need streams for it. I would like to do a little bit more computational archaeology and tell you about the Sieve of Eratosthenes. You may have heard of this. They often do this in some form of high school. We'll do it better, of course. So this is one of the earliest algorithms. It's a technique, a sieve, if you will, to build a stream of primes. So the basic observation is that 2 is a prime. Here we're going to start with 2. And any number greater than 2 is prime if and only if it is not divisible by any prime number smaller than itself. So we can use that observation to kind of use a sieve or a strainer to sift out the primes. And let me kind of illustrate the algorithm for you here. Let's see. So I want to, here's what we'll do. So here I've listed some numbers, And we're going to imagine a procedure, which I'll write in a second. And the first thing we do is we look at the head of this stream. And it's going to be 2, so we're going to output 2. Like 2 is going to be our first prime, which is good. Use a red pen for this. Okay, so we output 2 as being a good prime. Now, before we proceed, I want to filter out all the things greater than the number I just output that are divisible by it. So what I want to do is I want to take that head, which happens to be 2, and filter out all things in the stream that are divisible by the head, namely divisible by 2. So I'll run a filter operation. I'll take out all of these guys. So these are now deleted from the stream, and I'm making an infinite stream of just the odd numbers. Once I do that, and of course it doesn't have to terminate because I don't actually deliver that. I deliver a stream whose head is 3 and a promise to compute the rest. At that point, I recurse and I say, well, now I'm at 3. Output that as a prime, which is indeed correct. Before I continue, what I do is I now take the tail of the stream, which starts at 5. And what I do now is I filter out everything. Let's see, you can pick a different color to illustrate this. The possibilities are endless, folks. Oops, that didn't work. All right, the possibilities are not endless. The possibilities are extremely limited. We'll have to just make do with this. All right, so before continuing, I have to take the tail of this stream, which begins at 5, 5, 7, and so forth, and I need to filter out all things that are divisible by the head, which is, of course, 3 in this case. So let's go down this stream here and find all things that are divisible by 3 that are still in here. And the first one is going to be 5. I'll illustrate that like that. Not 17, not 19, 21, and so forth. And I delete all the things. I filter out all the things divisible by 3. Now I recurse. I find the next thing in the stream, which is 5. And I'm going to output 5 as my next prime. Before continuing on, I now take the tail of the stream, which at this point begins with 7, like 7, 9, 11, 13, and so forth. And I'm going to filter out from the tail of the stream all things that are divisible by the head, namely 5. So scanning all along here, a lot of things to delete already, but I will delete at 25 and continue. And finally, I'll stop by saying I'll delete 7, and the process continues.
Why didn't we delete 9 when we did divisible by 3?
Oh, yes, I should have done that. Mistake. Thank you. It's correct in the notes. It's not correct in my what I just did. Great. Great. Thank you for pointing that out. Apologies. Okay, so now it's all correct. Thanks for pointing that. Let's see. So we can look at this as a recursive process. You know, the head is in the result, and so the tail is filtered to remove anything divisible by the head, and then so forth recursively. So let's actually write the code for this. I'll put this down here. And by the way, if I made any mistakes or if there's handwriting issues, I've actually done this at least up to 3 down here, and you can check my work and make sure it's okay. Okay, let's define the sieve function using this process here. So sieve is going to be a function that takes a stream in, and of course the stream is going to initially be the integers. And it's going to basically animate exactly what I said. It's first going to just assume the first thing is a prime number, and it's going to cons that onto the output stream. And then it calls itself recursively here on what? Well, the result from filtering out all the things in the tail of the stream that are not divisible by the head. So here's the head. Here's my predicate. Is it divisible? There's the tail of the stream. So a very elegant way to define the prime numbers. Now I can define the prime numbers here as applying the sieve function to the integers starting at 2. Now, we're going to go over this in section, probably in some detail, but the basic idea of this is that using this code for streams, the first thing in the stream is 2, and then the tail of the stream has all the integers not divisible by 2, and so forth, just as I illustrated. So this, of course, is an example where you really need to understand the delays to make sense of it, and it's a great example to work through. So before section, take a look and see if you can try to work this out. Otherwise, we'll show you a trace of that in section. But it's a great exercise to do. Okay. So let's take a little breather before I do the next thing, which is, equally mind-bending in some sense. And I want to mention what I'll be doing on Wednesday. So we have now seen map, and we've now seen reduce. And around 2004, some Google programmers wrote a paradigm which is called MapReduce and used it for cloud computing and distributed computing. Now, this isn't a course on systems or cloud computing or distributed computing, but the interface to MapReduce is basically Scheme. And now that you know what MapReduce and reduce are, and you know how to do some functional programming, you would be able to use this interface to program millions or even tens of millions of computers just by writing essentially Scheme code. And I'd like to tell you the story of MapReduce and how it was developed and how it was used in the first few years and subsequently, and show you some slides on that, because it was basically something that was grounded in the kind of functional programming and high order functions we've been studying. And at this point, since you know both of those functions and have used them, it will be relatively transparent to see how to do that. I have to say there really isn't another good way to control and distribute a program quickly across tens of millions or hundreds of millions of distributed processors. And it's used widely in industry at this point, although there are even better replacements at this point. So that's what we'll do on Wednesday. And while the Scheme code on Wednesday could be something I might ask you about on a problem set or assignment, none of the distributed computing stuff would be actionable for something that I could ask you a question on, because it really is a pointer to advertise more advanced CS courses in the area of distributed systems and operating systems that you might be interested in taking at some point. So hopefully that will be enjoyable. Okay, so this is okay. All right. So we made the prime numbers now. But I want to do something else here that is kind of mind-bending, which is what you might call recursive streams. So how about if we define a stream in terms of itself? So here's integers from. We did not do that with integers from. Here in integers from, which I've reproduced in blue, we defined a procedure that returns a stream. But we can actually define streams recursively. So look at what I've done in blue here. I define ones to be stream cons of 1 onto the stream ones. And the stream looks like this, 1, 1, 1, 1, 1, 1, 1, 1, 1, out to infinity. So think about this a little bit. If we tried to do this with regular old cons instead of stream cons, right? Remember, stream cons has a delay in it like this, it would not work, right? Remember, stream cons remember that stream cons xy is exactly equal to cons x onto delay of y. So if you tried to do this regular cons, can't possibly work, right? Because, you know, maybe ones was already defined, they would try to stick a 1 onto that, or you get an error if ones is undefined. But stream cons delays its second argument. And it's just as easy to delay the expression ones as anything else. So now we have a great way to make an infinite stream of ones. Let's try to do something a little more interesting. Let's try adding streams. This is a pretty useful function here and kind of follows our paradigm for writing stream functions. So we add two streams, A and B. We check if they're empty, that's fine. If they're not empty, look what we do. Look at the call to stream cons, which of course will contain this delay. So the head of the stream cons is just adding the first of B and the first of A together. The tail is just a recursive call to add streams on the rest of A and the rest of B. So just to not put too fine a point on it, the call to stream cons, which is where the action is and where the delay is underlined in blue. In magenta is the construction of the head of that stream, adding first of A and first of B. The tail in red, which is going to be delayed, is a call to add streams on the tails of A and B. Using this, we can now define the integers. And of course, we'll do some detail about this. So look what I've done here. I've defined the integers to be essentially add streams of the ones and the integers, but before that, I stick a 1 on that to get the stream started because I need a value. So this is kind of the premier way to define recursive streams for things like integers like this. Basically add the integers together with ones. All right. Now, I've worked through this here, but I'm going to show you a couple of ways to reason about why this is correct. Hopefully we can erase that, why it's reasonable. Let's think about it here. You know what I want to do here? I think I want to just add a blank page so I can do a little writing. All right. Okay, so here's how I think of this. So again, we're going to take this beast here. I'll put it up here so we can think about it. Put it down here like this. So what does something like this mean? How do we make sense of this? Why would that be the integers? So I sort of think about it, I mean, intuitively it kind of makes some sense because you might imagine doing something like this. You might imagine saying, well, let's forget about base cases and assume we're sort of in the middle of things. We could imagine the integers look something like this. They look like 1, 2, 3, 4, 5, 6. That's the integers. And then the ones looks like this. So these are two infinite series, right? So this is ints, and this is ones. And we're imagine we're adding those two things with add streams. So we're adding two infinite series. And if we add two infinite series, we're going to get something that looks like this: 2, 3, 4, 5, 6, 7. Again, this is just intuition. Now, the intuition is useful here because it tells you why I had to start the stream with a 1, because when I add up these two things, this in the second form add streams, I get a stream starting at 2. This isn't really quite enough to convince us, but it's sort of the intuition. So let me write down the intuition for why something like this would work. And let's try to really work through it with delay and see why this would be the case. So the thing is, you might be wondering, well, are all these things defined at the time you're actually doing the addition? And what about the delays and so forth? So one way of thinking about this is to start with a summation that looks like this. So we have the integers here, and we have the ones here like this. Now, no matter what you think about these streams, it's pretty indisputable if you know anything about streams that int starts with 1 because there's a 1 right here in the definition. And if we go back to ones here, 1 starts with 1 as well because I got a 1 there. So those are literal things, those are actual values. So my case here to start this could look very reasonably like this. I'm going to have what I hope is an infinite stream. I'm going to add these up here and do a plus, and then I expect to have some long sum here. So I'll even state my aspiration like that. Okay. So I'm adding up these two infinite series, and all I know about them at this time is that the head of ints is 1. Why? Because I have a 1 here. And the head of ones is 1. Why? Well, because I have a 1 here, right? So that's fine. So it's pretty clear that they start with 1, and we know add streams looks pretty well formed. So now what I'm going to do is I'm going to add them up, and the result will be at the bottom, which is the way that I define the integers. So what I do here, remember what I'm doing is I'm actually defining ints by this recursively. So what I do is I take those two 1s and I add them, and I get a 2 here. Well, now that I have a 2 there, if I take stream rest, it's going to give me the 2 here because that's how I define integers. And the next 1 will be 1. So now I get a 3 here. Then I put the 3 up there, add a 1, and I get 4. And then I put a 4 up here, I get another 1, and I get 5. Put a 5 up there, add a 1, I get 6. One more time, 6, 1, and 7. So now I get my infinite streams as desired. So this is the intuition for how this works. And the way that I think about this is as follows. I think about this by saying that essentially, when I did my first computation here of +1 and 1, the delay was holding off everything to the right of this line. Like everything here was being delayed. So I'll say delay. Oh, get rid of that. Yeah. Apologies. Here's my line for delay. So what I say is delay is here, and everything here is being delayed right of that line. So remember, when I did this business with 1 and 1, there's stuff that's going to happen in the tails, but it's all being delayed. And then over time, what happens is that the line of delay gets moved. What happens? Well, this 2 moves up here, and then I plus them and I get the 3. And then the 3 moves up, and then I'm ready to operate on this. So at this point, what happens is the line of delay gets moved, and I can just move it over here like this. Next step, what I do is I basically have computed the 3, so the 3 goes up here to define that. The line of delay gets moved again. So the delay keeps moving out like this. One more time, we've computed the 4, and the 4 goes up here like this. And then the delay gets moved down. So you're delaying everything in the future, and you're just doing the immediate computation now. And so this is why this rather unusual way of thinking about it will actually produce for us a stream. But this graphic illustration, and I'll show you some pitfalls of this, is really, it's not really a proof. Closer to a proof is looking at boxes for the streams. So I'm going to do that now, which is just an orthogonal way or a different way of doing the same kind of argument. So let's look at our example here. I'm going to take this and move it down here. And let's try to draw our cons pairs to see what's going on here with integers from. So after evaluating this form, integers is going to be bound to something that looks like this. So I'll have a variable called integers, and I'll just call it ints here for brevity. Integers is going to be bound to a cons pair that looks like this. And the head of this is going to be 1, and the tail of this is going to be a promise to add streams. I'll use an abbreviation, ones and ints. And let's try to put a box around that to remind us we have a evaluated thing for a promise. Why is this true? Well, look at the code. Ints, or integers, is defined as stream cons 1, and that fully justifies the 1 as the head. The tail is add streams of 1 integers. That's delayed, so it's a promise. So after executing this form, integers is bound to this cons pair here. Now, the interesting thing happens is what happens if we say stream rest, I'll give you an SR of ints. Well, what this is going to do is it's going to force the tail. Now we have to go look at add streams to make sure we understand what it does. Let's go back to add streams here. Add streams is going to do a stream cons. So we absolutely know based on type from that we're going to get a cons pair back. It's going to be a stream, so the head will be some value, the tail will be some promise to do something else. What's the head? It's going to be the plus of the heads of the stream, and then the promise is going to be a promise to add the tails of the stream. And so what happens when you do stream rest events, we're going to return a value that looks like this. We add the heads, and we're going to get a 2. And now the tail of this thing is going to be a promise to add streams. A little more interesting, stream rest ones, stream rest ints. How did I get this? I just looked at the code, right? So looking back up here at add streams does the stream cons of the heads, and there's the tail is going to be a delay of the add streams of the tails, which are stream rests. So that's what happens after one stream rest here. Let's do one more. Suppose we said stream rest of ints. That requires taking this object here, and again, taking the stream rest of it. So what do? We force the tail. and we get an object that looks like this. Again, it's a cons pair again. The head is a 3, and the tail is a promise to add streams, stream rest, ones, stream rest, ints. Okay, and the pattern repeats. So pretty cool. Now we can define recursive streams, namely streams that are defined in terms of themselves, which is pretty nice. Let me set you up for some things that we'll do in more detail in section, but I want you to see now. So here is a way of defining Fibonacci numbers. So Fibonacci numbers are defined like this. There are two base cases, f of 0 equals 0, f of 1 equals 1. These come up all the time, by the way. They come up in online algorithms from the basis of most of the routing algorithms that underlie the initial version of Akamai, actually. So basically, online algorithms can't see the future, but they can make really good estimates. But f of n is defined recursively as f of n plus 1 plus f of n plus 2. So you could write a recursive function to do this, but streams implement this really, really well. Skipping over our thing here. So here's the Fibonacci numbers that implement this. Let's just make sure we get the mirror of the math. I think I'll copy this down here so we can really see it. Let's go down here, put the code next to the math. So you can see this. All right. So basically, in this case here, we basically need kind of two base cases to get things started. That's the first 0, streamcons 0, streamcons 1. They correspond identically to the base cases that define the Fibonacci sequence. So the basic idea of Fibonacci sequences is that, when we ask for the third element, add streams adds the first and the second. The tail then is a promise to add streams of stream rest of Fibonacci and stream rest of Fibonacci. And you can see that here. And that's going to basically generate the f of n plus f of n and minus 2. So pretty interesting. Again, two base cases isn't just restricted to weird things like the postage stamp problem. It actually comes up a lot in mathematics. And I think you can see how closely the scheme code mirrors the mathematics in making things like this work. All right, so that's most of the technical content I wanted to talk about. I wanted to segue into some issues you have to be careful about. So it's pretty easy to make what we call, these are very powerful. It's like what Spider-Man says, with great power comes great responsibility. So it's super easy to make what you might call divergent computations. So these are streams with nothing in them. It's different from the empty stream. An empty stream can't even detect them. It's actually intractable to detect these things. So suppose I define this function here called lose. What I do is I first filter out all the even numbers and the integers, and then I filter out the odd ones. So lose, if you try to execute this, anything that gets past the first filter won't pass the second. So this runs forever, trying to find a number that's simultaneously even and odd, because it doesn't know that. So this is pretty deep question. We don't want to have divergent computations like this. So you have to be really careful with streams so you don't make things like this, that you have all this power. And similarly, we have to be very careful with our reasoning about streams so we don't get into some strange conclusions and paradoxes. And to this end, what I'd like to do is I'd like to show you a little video from Numberphile. And as I mentioned at the beginning of class to some of you who came early to chat, I had some technical setup that I think will work to do this. Let's just see if it really does. So I'm going to stop sharing the screen. And I'm going to now show you the Numberphile thing, and we'll see if this actually works for us. And by the way, if for some reason the resolution isn't good or some other kind of problem, then I will ask you just to look at this on the course website where I made a link to it. So let's look at this, then I hope we can maybe have a short discussion about what you thought of the video you can let me know your opinions about it. Also, happy to take these questions offline, i.e. office hours, after class, or piazza. So again, the connection here is that for us, streams are a form of infinite sequences, like the integers of the primes, but there are lots of other infinite sequences. They arise all the time in mathematics and physics and computer science, and some odd things that can happen that also, at least to a mathematician, are quite amusing. Let's watch this number file video together. If you have trouble, hearing the sound or something, I think I've set that up correctly, let me know, and I'll try to do something about it. So let's see if this will work.
I'm going to give you an astounding result.
Astounding.
An astounding result.
So I'm just going to write down a little sum, and we're just going to see what answer it gives. 1
plus 2
plus 3
plus 4
plus and I include all the natural numbers, so all the way up to infinity. So what do you reckon the answer to this is, Brady?
Well, I would say it would tend towards infinity.
Yeah, that makes sense, doesn't it?
The answer to this sum is remarkably minus a 12th. It's amazing. I mean, I first saw this result when I started learning a bit of string theory.
And what's even more bizarre is that this result is used in many areas of physics.
This is a very well-known string theory textbook by Joe Polchinski. As you can see, sort of quite early on, page 22, we have this statement here, which is that the sum of all, this is basically saying the sum of all the integers, or the natural numbers, all the way up to infinity, is minus a 12. All right, so we're going to prove now, without getting our knickers in a twist with Riemann zeta functions, we're going to prove quite a simple way why the sum of all the natural numbers is indeed minus a 12. So to do that, we're going to do this in a number of steps. We're going to look at a few different sums. The first sum that I want to look at, I'm going to call it S1, and it's 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. That's the first sum I want to look at in principle. The second sum I'm going to look at is 1 minus 2 plus 3 minus 4, and so on. Just carry on in that process all the way up. And the third one is, of course, going to be our one that we're really interested in, which is 1 plus 2 plus 3 plus 4, and so on. So we're going to evaluate all these three different sums. Now, the first one is really easy to evaluate. We need to attach a number. Now, clearly, what is the answer to this? Now, you stop this at any point. Okay, if you stop it at an odd point, you're going to get the answer 1. If you stop it at an even point, you'll get the answer 0. Clearly, that's obvious, right? So what number are we going to attach to this infinite sum? Do we stop at an odd or an even point? Well, we don't know. So we take the average of the two. So the answer is a half. There are other ways to prove that this sum is a half, by the way, which we can do if you want. But
No, there'll be a link. There'll be a link there because we've done it before.
Okay, good.
So you'll see the link there.
Okay, so this is a half, but I think intuitively that's the easiest way to see it, that you either get 0 or 1, and therefore you just take the average. So this is the natural number to attach to this sum. But once we know this, we're laughing, okay? Because from this, we can achieve everything that we want to achieve. The next step is to find out what this sum is. So what I'm going to do is, I'm going to take 2 copies of this S2. Okay, so I'm going to add it to itself. So 2 times S2 is equal to, well, let me just write it out. So I'm going to write it out twice. 1 minus 2 plus 3 minus 4, so on. And then I'm going to add to it itself, but I'm going to shift it along a little bit. So that's plus 1 minus 2 plus 3 minus 4, and so on. Okay, I've just taken 2 copies and added them together. But I've done it in a particularly nice way, in that I just push this one along slightly on the bottom. So now you see what you get. You take this one and this and this, and I get 1. So 1 plus nothing is 1. Minus 2 plus 1 is minus 1. 3 minus 2 is 1. Minus 4 plus 3 is minus 1, and so on. And I'm going to keep getting this pattern. So hang on a minute, I've just got back to sum that I started with, which I know the answer to. So half. Okay? So therefore I know this sum now. Because I just divide through by this 2 and I get a quarter. So now I know that this sum, this second sum with somewhere the signs alternate, is actually equal to a quarter. So this is my second remarkable result. Now I have everything I need to prove this crazy minus a 12 thing, right? Okay, so let's do it. I'm going to take this one and I'm going to subtract this one. Okay, so I'm going to subtract S2 from S. Well, let's write them out again. Okay, so I'm going to write out S first, which is 1 plus 2 plus 3 plus 4 plus 5 and so on. Okay, and I'm going to subtract S2. So that's minus, okay, let me just put a bracket in now because I'm going to minus all of this. 1 minus 2 plus 3 minus 4 and so on. Okay, okay, 1 minus 1, what's that?
0.
0, yeah, exactly. So I get nothing from that bit. 2 minus minus 2 is 4. Okay, 3 minus 3, 0. 4 minus minus 4 is 8. And so on. And the next one, I'm going to get, from the 5s, I get nothing. From the 6s, I get 12, and so on. And it proceeds in that way. And now you can see we're almost there now, right? Because look what I've got here. I've got 4 plus 8 plus 12. If I take a factor of 4 out, it's 4 times 1 plus 2 plus 3. Okay. It's my sum that I wanted. So now I've got a formula for my, so this is just 4 times S, which is my sum. So now I just solved this equation, right? Because I know what S2 is. So I have now the expression S minus, because I know what S2 is a quarter, is equal to 4S. Okay, I take S from either side, so I get minus a quarter is equal to 3S, which implies that S equals minus 12. So now do you believe me? That's amazing, I love it. It's amazing. Who'd have thought?
Tony, if I got a calculator out and wrote 1 plus 2 plus 3 plus 4 plus 5, and I sat here until the end of everything and then pressed equals, would I get minus a 12?
I actually mean the end of everything. You can't do it to the end of everything, can you? So, see, the point is, I know this looks like a bit of mathematical hocus pocus sort of thing, but actually, in truth, it's not. And I'll tell you why we know it's not. We don't, and I know you think I go on about physics too much, but we know it's not because of physics, because these kinds of sums appear in physics, and in physics we don't get infinite answers. It's amazing, and it's just, do you know, I was trying to come up with an intuitive reason for this, and I just couldn't. To be honest, it's just, you have to do the mathematical hocus pocus really to see it. And then you just have to believe that you're not measuring physical infinities in nature. And then those two facts together, I think, give you confidence in this result. But it is clearly counterintuitive, and it's counterintuitive because, you know, intuitively you just want to stop the sequence. And the minute you stop the sequence, then all your intuition for this result goes out the window.
So if I do 1 plus 2 plus 3 plus 4 plus 5 and I go up to a Googleplex,
you'll get a big number. Yeah, you won't get anything like minus a 12. You have to go to infinity, Brady.
It's negative. I've added all these positive numbers together up to infinity, and I've got minus a 12. But it does play a role in lots of different things. There's the number 12, and it's, so for example, as I said, the calculations of the critical dimension in string theory, the 26 dimensions, comes from this calculation.
All right, what did you all think of that? Any reactions?
Pretty interesting.
Mind-boggling.
Yeah. It's pretty hard to get your head around. So I guess the main point for us is like, wow, infinite series streams, pretty remarkable, strange things that you can get strange results from. So I put some references on the webpage about this. This is actually connected to something called Riemann zeta functions, which you will study probably in last year of a mathematics class. And if you were to be a math major. And I should also mention there's a nice analysis by Terry Tao, who's one of the youngest people ever to win the Fields Medal, who kind of gives some intuition for it. There is a way of thinking about this. Would like to suggest, this won't be on any tests, of course, think about it, and we can ask questions maybe after class or at another time after class. I can, maybe give you a little intuition if it's confusing or mind-blowing. Certainly blows my mind. But let's do a few other things and have some more discussions. Just want to mention a few other things that are a little bit mind-blowing about this. I'm going to let you read this part yourself, but what I basically want to say is that if you have streams and you mix them with assignment, like set bang, you get some very strange effects. It's kind of like drinking and driving. It's really super dangerous. And that's one reason we don't like to have side effects in functional programming. But there's actually debate between functional and imperative programming, and you might even be having that among yourselves or with your other teachers or somewhere else. So, in functional programming, all functions are really like mathematical functions, and scheme doesn't have set bang, or we don't really use it. Substitution model semantics. But of course, the imperative style, pretty standard, right? You have assignments, object orientation. So, the baron of functional programming says, hey, side effects cause lots of problems. Give them up. They mess you up. You can't think straight. But the imperative programmer says, look, I'll be really good. I'll just use side effects for local state, like object-oriented style, very few global variables, but I really need that state. I can't do the program without it. Someone will tell you this probably. The functional programmer says, have I got state for you? Look at streams. I've got all this great stuff. I have a stream. You don't need hidden variables. I have a bank account with an infinite stream of transactions and resulting balances. Each new transaction comes along and the balance changes. So I have a beautiful thing like this. So stream is a beautiful model of the transactional history of, say, financial records and things like that. Well, what about a shared account, picking two of our TAs? Suppose Jessica and Nicole are going to share a bank account. Well, they somehow have to merge their requests to the bank. So you can't alternate, then Jessica can't deposit money and immediately withdraw it. She has to wait for Nicole to do something in between. Maybe Nicole is in another state or in class and not at the bank. So there's this notion of fair merge. How do you merge a series of streams of requests, one from Jessica, one from Nicole? It's really complicated to define what fair merge is in some sense. If one is ready, the other isn't, take the one that is. All of a sudden, the notion of state and time has re-entered. This merge box really knows about state in some sense. It knows who's gone last or, who's waiting. It's not really functional. So this debate is not really even over. And this comes up all the time in real life. I don't know if you've ever been to parts of the world like New England or parts of the West where there are one-lane bridges over gorges and things, but someone has to wait. And sometimes people are bad and don't let people go, right? So the notion of fair merge says you eventually get to go, but you want to go after some finite amount of wait instead. There's the pastry shop algorithm. Says you're in New York City and you have delicious pastries and you want to go in for, delicious hamantaschen or something. What you do is you take the first 15 people and you serve them, and you kick them all out, take the next 15, right? You have to have some state for that. You have to be able to count to 15 to do it. So we don't really have a good way to do this. This is an active area of distributed systems to think about this. So the debate between functional programming and imperative programming comes to a head. The front lines of this involve infinite objects like streams. And if you go on in computer science, you'll learn that most people reason about these not only using induction, but a more advanced technique called co-induction, which we will not cover in this class. So in short, to think about this, really what we have in this case is we have delayed evaluation, lazy lists in some sense. It's a super powerful tool, allows certain of our abstractions to be super efficient. It behaves very badly with assignment, terribly. I won't show you that, but it is in the notes. But you could also view state as the time evolution of a computational process and package up the state in terms of a stream. But from a mathematical point of view, a really cool thing about this is that we can now have infinite objects and pass them around as first class objects. So we can have a variable that's bound to the integers, even though that's infinite, or the rational numbers, or the prime numbers, or the odd numbers, or the even numbers, the numbers divisible by 3, the Fibonacci numbers, any of those things can be a stream as long as we can define an order on them. So basically any inductively defined set can be used to define an infinite stream, even if it goes on forever. And now we can reason about those. And in the same way that you could have math problems in calculus and pre-calculus where you had infinite series and you had infinite sequences and you asked what would happen with those things, now we can have computational processes that reason about those and compute about those that are basically as good as the processes that you developed by hand in mathematics, which is pretty cool. So this is essentially for y'all, it's a new data structure. It's a data structure that lets you operate on and represent infinite objects, such as infinite sequences, infinite series, and so forth, and which is pretty neat. So, you know, later on, we can imagine doing some things, and I think I might even give you this example, where you might have the integers, and I take the square root of the integers, whatever that means. It means apply the square root to all the integers in some sense. And if you were going to, what's the next holiday? Thanksgiving, either remotely or with your family, and you tell them that you learned to take square root of all the integers, I mean, they probably would think you're working a little too hard. But in fact, square root is just a function. The function can be defined to operate on any number. We now apply that to all the stream using map streams, and the notion of taking square root of all the integers becomes relatively straightforward. And so this is, again, a paid commercial advertisement. And we'll go into that a little bit later. So that's really what I wanted to tell you about streams, other than giving you a fair bit of practice with these. But let me just make a couple of points in our remaining time. What time are we getting to here? Oh, I have a couple minutes. Just to sort of summarize. So let me add a page here again and just draw for a little bit. All right.
You're not sharing your screen.
Oh, I'm sorry. Thanks. Hopefully we didn't miss a lot. Unless I was just scribbling. I'll share my screen now. Thank you for reminding me. All right, I appreciate it. So these notes are on the web, but what I meant to say was, let's see, we did divergent computations. We skipped that. This was basically talking about the bank accounts for Jessica and Nicole. So the key example here is you have to merge the requests. I summarized down here by saying that we have to find a way to think about how to deal with this notion of state, and I sort of summarized down here like this. Let's go back just to summarize where we are in another sense. I'll just write a few things. So one of the main things we saw is that actually all of streams can be implemented with lambda. So we saw a couple of lectures ago that lambda can be used to implement cons. And we saw that lambda can be used to implement delay. So in some sense, lambda is a constructor. It's used to construct other things. And this is really the reason that when we defined it, I mean, from my point of view, we could have initially called lambda something like make procedure. So we could have said it returns a procedure, which is actually correct in terms of type. But the fact that we can use it to construct other things, not only like the Y Combinator, but we can use it to construct cons, delay, and so forth, means that we can make and represent all sorts of very sophisticated objects. With cons, we basically get almost all data structures. With cons and delay, we get actual streams. So given the two together, when we make streams, we can actually now make infinite objects like the integers, model some primes and so forth. And the key to this sort of under the hood was the ability to have lambda as defined here. Okay, so let me pause by just saying, I'm sorry my screen wasn't shared for a couple of minutes. Let me say where this is in the notes if you want to review. We talked about divergent computations. That was the number file video. There's some text that I skipped on, did not cover, which is in green here, on what happens when you try to mix assignment and streams, which is a bad idea. Then I sort of talked through this debate of functional versus imperative programming. And the example was in this diagram here. If I have a stream of transactions going in over here, I could have a stream coming out, which are the balances. but there are issues when you have two people sharing an account because you have to merge the requests sometimes. So the key thing to take away is that I could never assign you without some guidance the task of writing this merge function, because you need some assumptions and performance criteria to figure out how you would actually merge two infinite streams. You can't just alternate, and are you allowed to have state in there? So a good question is to think about in this example is how would you actually go about thinking about merge? And if you can think about that, that gets you to the foothills of what a lot of people in the areas of systems and operating systems think about in some sense. So the debate between functional and imperative programming is still ongoing because essentially we don't have a good answer for which is better in all cases, because sometimes you do need some state. So again, to summarize again, we had streams, infinite streams, delayed evaluation, pretty cool things to be able to model these infinite objects. And even in this first lecture today, we did the integers two ways, the primes, the numbers divisible by 3, and a few other interesting things like the Fibonacci numbers. And we'll do some more examples in section and then various assignments we'll give you. And now you know how to make infinite streams and pass them around as if they were data structures. So I think with that, especially given the time, I will stop and take questions, and I will also stay around afterwards in case anyone wants to chat with me and anyone who wants to have a discussion. Feel free to go whenever you want, but if you'd like to stay and ask questions, please do, and I'm happy to do that.